the efficiency up, really is of interest. Also, we see new applications like the eVTOL, electrical vertical takeoff and landing aircraft, or air taxis. Those really didn't exist before silicon carbide. So Microchip's been involved with SiC for over 20 years. If you look on the left, we shipped the very first devices in 2003. And in 2006, APT, or Advanced Power Technology, was acquired by Microsemi. And around that time, APT was looking at hybrid modules, which included very fast IGBTs and co-packaged silicon carbide diodes. And early on, they saw the need for much better packaging, getting some of the inductance out, allowing those diodes to perform at a higher level. In 2018, Microsemi was acquired by Microchip. And since then, we've come out with a bunch of new devices, including 3.3 kV silicon carbide MOSFETs and Schottky barrier diodes. So when you look at SiC and silicon, often people say, wow, that SiC device costs more than the silicon equivalent, but they aren't really equivalent. And to create a silicon carbide wafer, it's not as easy a process as it is in silicon, so actually the starting material is much more expensive. But when you design with SiC, your system cost drops way down. You take advantage of the higher switching frequency, the higher temperature capability, and now your system cost is below a silicon-based implementation. In addition, it can be more efficient, more rugged, last longer, also smaller and lighter. Here's a great example. On the left, we have a trench 4 fast IGBT module. On the right, we have a silicon carbide MOSFET module. If you look at their datasheet ratings, the IGBT module is rated at 500 amps. The silicon carbide is rated at 173 amps. They're both rated at 1200 volts. But if you start looking at their package sizes, the IGBT module is about 3 times the size of the silicon carbide module. And if you look at real applications, if they're switching at 30 kilohertz, you can see that that 500 amps now drops down to 130 amps. The 173 amp SiC MOSFET module also drops down to 130 amps. So now they're at parity. And if we push the switching frequency higher, which silicon carbide really likes to perform at the higher frequencies, now that 500 amp module is rated at 60 amps, the silicon carbide module is almost twice that at 115 amps. So if you look at the package size being a third smaller, having twice the current, you have about 6 times the power density. And if you look at the switching losses, the IGBT module is 16 millijoules versus only 3.4 millijoules in the silicon carbide MOSFET. This is one of the reasons why silicon carbide can outperform silicon devices. Here's a great example, the packaging evolution due to silicon carbide. The TO247 package has been a workhorse in the industry. A lot of silicon power devices are using this package, but when you start switching really fast, you start finding limitations of this package. So this 3-lead TO247 has evolved into what's called a 4-lead TO247. So a new lead was added. It's the sense source. If you look at the diagram on the right, basically you're bypassing a lot of the parasitic inductance in the circuit. This allows much faster switching. With that faster switching means you have less losses. And in this case, at 50 amps, using the same die, silicon carbide die in both packages, you can reduce your switching losses by almost 70%. Pushing beyond the TO247, we have a couple additional examples of great packaging evolution. This common source sense lead that's been added, you can see it in the D2 pack. Using the same silicon carbide die in the TO247 above, you can see we've reduced the switching losses quite a bit in a D2 pack. Also, the PSMT, power surface mount topside cooled, not only does it have the source sense lead, but it also incorporates better thermal performance. You can think of this package as almost upside down. The die, the backside of the die faces up. This allows you to mount a heatsink directly to the top of the package. Now you're extracting heat out very efficiently and effectively. Versus if it's soldered down onto a circuit board, maybe it's FR4, Even if you have thermal vias, they're going to get limited performance. And with silicon carbide, it likes to perform at a higher temperature than silicon does. So often you'll see people pushing the capabilities thermally of these devices too. Modules are also taking advantage of silicon carbide. In this case, we have an SP6Li module. Li stands for low inductance. The module has extremely low inductance, less than 2.9 nanohenries, which is probably about the lowest in the industry. This module was developed specifically for silicon carbide MOSFET technology. It allows you to switch at a higher frequency. You can run at higher voltage. It's higher efficiency. Part of that is with the low inductance, you have less of an offset between the terminals and the actual die. Typically, there's a voltage differential there, and your bus voltage, which connects to the terminals, has to be reduced so that the voltage on the die is not exceeded. This means you run less power through the package. If I can reduce that offset with less inductance in the package, I can run at a higher voltage, or I can run higher current through it. It has less voltage overshoot. This is an example of an SP6Li versus a TO247 implementation, both basically rated at the same value. In this case, one SP6Li is equivalent to 36 of the TO247 packages. If you look at some of the performance on it, the stray inductance, the SP6Li is 2.9, almost 3 nanohenries versus the TO247s being around 20 nanohenries. And if you look at the cost, the module is just marginally more expensive than the discrete implementation. But the discrete implementation is going to take a lot more labor to solder those TO247s into the board. Also, each one's going to have to be connected to a heatsink. That's very labor intensive. One thing about Microchip, they design and manufacture their own modules. That's important because often customers have very specific needs. They may want a different substrate, different base plate material, or maybe there's an internal PCB layout that they need a little bit different to optimize their applications. Let's now take a look at some performance comparisons between the D3 62 millimeter and the SP6Li modules. Both have the exact same silicon carbide die in them. If you think of the silicon carbide die, it's kind of like a racing motor. And if you put that racing motor into the D3 module, it's kind of like putting the racing motor into a four-door sedan. Yeah, it goes a little bit faster, but you're really not able to take full advantage of it. If you think of the SP6Li module, this is more like a Formula One racing chassis. So you take that racing motor, you put it in there, this allows it to perform at its full potential. The D3 module has about 15 to 20 nanohenries of parasitic inductance, while the SP6Li is down to 3 nanohenries or 2.9 nanohenries of parasitic inductance. Packages with extremely low stray inductance have multiple benefits. One is reduced voltage overshoot. In this case, we have the D3 versus the SP6Li, both with the exact same silicon carbide die in them. The bus voltage is at 900 volts and at around 75 amps. You can see the D3 has about 200 volts of overshoot versus about 120 for the SP6Li. As the current ramps up, that delta starts to increase. At 420 amps, we see the voltage overshoot of the D3 being 400 volts, while the voltage overshoot of the SP6Li is only 250 volts. These are, again, using the exact same silicon carbide die. You really see the differences that the low stray inductance can make to make this overshoot much smaller. So what can I do to take advantage of that? One possibility is I could look at even using a lower voltage device without exceeding my SOA of the device or of the application. The other is I could even run at a higher bus voltage. That means I can get more power through the same package. Another advantage of packages with extremely low stray inductance is greater efficiency across a wide range of working conditions. Here we show 10 kilohertz, which is a relatively slow switching speed, especially for silicon carbide. Here we're comparing, again, the D3 with the SP6Li, same silicon carbide die in each package. we see less switching losses in the blue line, which is the SP6LI, versus the D3 package. As we increase the switching speed, we see that delta increase quite a bit more. Again, dotted line is the D3 package, the blue line is the SP6LI. And pushing it to even higher levels, 50 kilohertz, you see quite a big spread between the losses of the D3 package and those of the SP6LI with the low inductance. Total switching losses can be 20 to 40% lower with extremely low stray inductance power packages. An added benefit of packages with extremely low stray inductance is their reduced cost of ownership. Let's consider two different systems. One with a D3 module, the other one with an SP6LI. Both running at 420 amps at 50 kilohertz. If you look at the dotted line, these are the megawatt hours of losses that you would have over 1 year, and they are losses, compared to the blue line, which is the SP6LI. The delta will be your savings. If we look at the 420 amps, far right, you're saving about 5 megawatt hours. And what does that mean? Well, in 1 year, if the cost of electricity is 11 cents per kilowatt hour, you'll save $1,100 per module. That's about the price of the module. And when you look at this reduction in energy consumed, basically losses, the SP6LI is really a cleaner, greener way of processing power. There was a great example presented at the Power America 2023 Summer Workshop of where silicon carbide power packaging is headed. In this example, they compared a conventional EV charger or fast charger with a silicon carbide based one. And if you look on the left, you see a green box. That's a transformer. Basically, three-phase, 4160 in, 480 volts out. That feeds into the power converter, which is a 480 volt in, and then it's a DC out, medium voltage fast charger. To the right, we see a silicon carbide implementation, much smaller. It's about a quarter of the weight and about a tenth the volume. If you look at the efficiency, if you look at the transformer, peak efficiency 98.5%. The power converter is going to have a peak efficiency about 95%. You multiply those together, you get 93.6% peak efficiency of that system. Compared to the silicon carbide, which is basically connecting directly to the 4160 volt line with higher voltage SiC devices and a solid state transformer, you're looking at 97.6%. Again, the system on the left is 93.6. The system on the right is 97.6% efficient. So you've gained 4 points of efficiency in the silicon carbide solution. Also, you don't need to pour a concrete slab to mount my transformer on. Maybe you have some conduit under the ground feeding the charger. In this case, you can have this unit pole mounted, which makes it a lot easier to deploy, especially in areas where it's very congested and there's not a lot of space available. In addition to the software simulation tools, we're seeing an emergence of hardware tools that help designers take advantage of state-of-the-art SiC power modules. This helps them assess the performance of the module, most specifically for their application. As an example, the SP6LI EVB, or evaluation board, is a compact evaluation platform that helps designers evaluate and optimize their switching and performance characteristics under controlled environment. Recently, there was a live stream put on by Microchip and Tektronix titled Dyno Testing State-of-the-Art SiC Power Modules. This live stream showcased the SP6LI EVB, and live demonstrations were done on how you could enhance the performance, tune the low inductance SP6LI EVB for specific application needs. In summary, we see there's a broad market acceptance for SiC, and that does save costs at the system level. And to get more out of SiC, new packaging is required to make systems more efficient, compact, and longer lasting. Today, we looked at the impact of parasitic inductance in power packaging. Comparing the SP6LI to the common 62 millimeter package, the end user can save over $1,000 per module per year. Just imagine a three-phase system, and multiple of these connected to the grid, you're not only saving money, you're saving power, which creates a cleaner, greener solution. And the SP6LI solution is superior to discretes and suitable for multi-megawatt scale power levels. I'd like to thank you for listening and finding out how you can adopt SiC with ease, speed, and confidence.
Thanks for that presentation, Perry. That was really interesting to see the comparison of SiC versus the IGBT and see the different packaging styles. Very interesting. Now we've got a few questions coming in from our audience. Are you ready to take a few questions and provide some answers?
That sounds great, David.
All right. So our first question says, can you tell us about some of the design trends in the SiC discrete power packaging?
Yeah, discrete, we're seeing more of a push toward the surface mount